All right, welcome everybody. First day of school. This is atomic physics. And those of you who don't know me, I'm Ivan Deutsch. So let's see. First things first. There will be. This is the last piece of paper that I will hand out in this class, because all of the information for this class will be distributed through the website for the class. Okay, and you can. I will email everyone who's registered for the course, because then I have your email address on the registration list. The link, but you can find it on the department's website. Okay, so there's a list of classes, and that has everything on it. So let's see. So some first administrative details about the course. So this is an advanced graduate course, and so really it's up to you from my perspective, to get out of this class what you want to get out of this class. And I assume you're here because this is a subject you're interested in and you'd like to get as much as you can. So as far as the course requirements go, although you may have seen otherwise, I've made a decision. There won't be any exams in the course. There'll be problem sets, which will be approximately every other week. We'll see how it goes, and there will be, and they will be worth 70% of your grade. And then there is a final project, which will essentially be a kind of term paper on a subject of interest to you, and that will be 30% of your grade. So as far as the requirements go, in terms of your grade, that's what it is. As far as the material for the course, as it comes, I will post my lecture notes on the web. In addition, we have our great cinematographers here, award-winning, and we will post a videotape, a part of the MP4 for streaming for you to review for the courses as well. Okay. There is a textbook that I called a required textbook, but it's not really required. Again, it's up to you. The textbook is a textbook by Phys. It may just be called Atomic Physics. Let's see what it's actually called. Yeah, it's called Atomic Physics. It is not quite at the right level for this class. It's more of a, and it's as discussed in the preface to the book, it's more of an undergraduate text than a graduate level text. But it covers the range of topics that I'd like to cover for the most part in this course. Chris is a experimentalist at Oxford, working on bosons and condensation and quantum control. And so he's what I would call a modern atomic physicist. And that's really what this course is intended to be. Now, of course, that's a pretty loaded word. You know, I'm a modern kind of guy, but, you know, one person's modern, another person's old-fashioned. But my intention here, this course, if you look in the course catalog, the actual title for this course is Atomic and Molecular Structure. It's a little bit of a leftover of olden times. And my intention here is, I've taught a course like that about 5 or 6 years ago. It's the only time I've taught this course before. It was really just a structured course. But I decided to change shift gears a little bit. So this course is going to involve a number of topics beyond structure. We'll spend about 1/3 of the course on basic atomic structure. We'll spend about 1/3 of the course talking about the interaction of atoms with electromagnetic fields. A subject which is covered in many courses, including in quantum optics. Those of you who were in quantum optics about a year ago whenever we taught that, I don't remember anymore. There'll be some overlap there, so it's always good to see some things again. And then we'll spend about 1/3 of the semester talking about laser cooling and trapping. And if we get to it, hopefully, Bose-Einstein condensation and degenerate quantum gases. All right. So that's the intention for the course. TAs for the course will be the students in my group, so you can harass them, even if they're in the class. And we'll work out a grading scheme. Let's see. Finally, I will plan to have at least one office hour, if not an office hour and a problem session or something, to help work through the homework. And so I'll be polling you over email to get a sense of when we might be able to do that, so that we can get the most people available. All right. So, anybody have any questions at all? As far as the textbooks go, so I should say beyond the book by Chris Foote, there is a book that I call the secondary text here. I meant to bring these to class today, but I'm sorry I forgot. It's a book by Branson and Yohanian. It's called Physics of Atoms and Molecules, and it has a lot of more details in it. It's a book about this thick. Well, of course, it has atoms and molecules in it, but it has a lot more details in it. It has quite a different emphasis, but I do recommend it. You know, it's really a question of what reference material you would like to have for your own library. So I won't be following any textbook in any very rigorous order. I have my own idiosyncratic preferences for how to present things. So, but nonetheless, we'll be referring to those things. All right? Okay, well, we'll get started here. All right, so let's see. We're talking about atomic physics. Now, atomic physics, I would say, has kind of two streams associated with it. There's the stream I would call understanding what nature gives us, and the stream, what can we do with nature? And at some level, this dichotomy appears within the AMO physics community. There's a big part of course, atomic physics was what understanding what atoms were, you know, at the end of the 19th century, beginning of the 20th century, is what gave birth to quantum mechanics. The Bohr atom is what I I would say, the important conceptual picture that gave birth to quantum mechanics and everything that followed it, of course. And this birth, of course, led to the whole history of 20th century physics. I mean, the Rutherford experiment, understanding the nucleus by scattering an alpha particle, you know, that's the LHC, is its descendant today. So understanding what the constituents of matter and fields are, understanding the fingerprints of the universe, astrophysical studies, all of that is an important stream of atomic physics. But there's another stream that has evolved over time, I would say more in the latter part of the 20th century and into today, which is the question of quantum control. So, the idea now is, well, we have atoms, we understand their structure to some degree. How do we control those atoms in such a way that we can perhaps use them for practical applications, something as practical as a quantum computer, if you call that practical. Hopefully someday it will be. Or also for further explorations of fundamental physics. And there's a little bit of a feedback loop that goes on in the way physics research happens that I think is quite interesting. You know, quite often what I would say is we have, you know, the complexity of nature. Whatever that is, which we then try to form simple models for. Our spherical cow. Or something equivalent. We might want to think about the binding of electrons to nuclei in atoms, and the first thing we would do is might say, well, let's think about a particle in a box, and think about what is the essence of what goes on when you're thinking about binding. But then, once we have our simple models, we try to, maybe nature doesn't provide those simple models, but maybe we can engineer, I'll use that in quotes, not disparaging, nature to look like those simple models. So for example, you know, we have a particle in a box, but then of course we that's really not what an atom is, but a quantum well in a solid state structure is engineered so that it behaves in that very simple way, because then we can control it. And then once we do that, we try to make those things complex again in a different kind of way, not necessarily what nature gives us, but using nature to be able to explore complexity. So in the context of atomic physics, this is going on as well. We have, for example, simple models of high-temperature superconductors based on thinking about electrons hopping around on lattice sites. And, well, that may or may not be a model that represents in any essential way a high-temperature superconductor, but maybe it does. But how would we know? Well, it turns out that that's a problem that can't be solved. We can't simulate it in any efficient way on a computer. We might say, well, write down this model, this simple model. But instead, what we can do is engineer a set of atoms to look like electrons, because they satisfy the same sets of dynamical equations hopping around instead of on the ionic lattice of cuprate, instead we have atoms hopping around on trapped lattices, which look like the same physics of the electrons hopping around in a solid. So there's this interesting, I would say, kind of Krebs cycle, a cycle of life that goes on here within physics, in which we do both. We're interested also, what is nature? How do we understand the secrets? And then we want to simplify them, use that, and sometimes we use those simplifications to create our own complexity. And that's sort of the essence I hope to convey this semester. But to do that, we were going to sort of need to start with this side. And of course, there's a lot one can say, and one can have people devote their careers to this. I should say one other aspect, another important part of this stream of what nature gives us. Although when we think about atoms, typically we're thinking about basic electromagnetic forces, Coulomb, attraction, binding electrons and nuclei. Perhaps we're thinking about magnetic interactions of spin, magnetic fields, but basically those are the forces. But the other forces in nature do perturb atoms. So the weak force is there and is coupling to the electrons. The Z boson is there doing something. And so an important stream along here is understanding not just the structure of atoms, but understanding other fundamental forces by being able to do very, 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 very precise measurements of what is the energy levels of complex atoms in order to perhaps look for parity non-conservation, look for a permanent electric dipole moment in an electron, things of that nature. So fundamental physics continues to be explored in atomic physics as well. All right, so with that general picture here, we begin thinking about the question of the structure of matter and the structure of atoms. So what's the first thing we do to get started? First thing you do, no matter what the physics problem you're doing is you think about scales. If you're doing physics, the first question you should ask yourself is, what are the appropriate scales in the problem? Are we talking about nanometers? Are we talking about angstroms? Are we talking about EV? Are we talking about Kelvin? What is the scale of the various physical quantities? The first question you should ask yourself, no matter what physics problem you're thinking about. And how do we determine what those scales are? We need to think about what are the characteristic units. So one of the most important tools we have as physicists is that we can think about the general nature of the problem rather than just the specific nature. So we want to think about characteristic units, and these characteristic units, of course, is what we call, when we're talking about atoms here, are what we call atomic units. So if you're doing atomic physics, there's always something called atomic units. So how do we determine what are the characteristics of atoms? Well, here, in talking about atomic, the notion of an atom is, of course, a fairly general thing. For example, I could think about the binding of a proton to a muon, or the binding of a positron to an electron. All of those you might call atoms, but for the moment when we talk about atomic physics, what I want to talk about is, for the moment, standard matter. Meaning something out of the periodic table, or something close to that. So when thinking about this, the star and player is the electron. When we talk about atomic physics, it's really the properties of electrons that determine. The nucleus can play some role in that. There'll be other characteristic units that arise when we think about the nucleus, but the electron really is what gives the coarse properties, the most important properties of atoms. And of course, the electron is specified by two things: its charge and its mass. So atomic units are going to depend on what we can do with charge and mass. Well, there's one other characteristic constant when we're talking about quantum mechanics, and that's, of course, h bar. So if we're talking about quantum mechanics, and for the moment we're talking about non-relativistic quantum mechanics, if we have relativity in the mix, then of course we also have the speed of light to work with, but for the moment we're thinking about non-relativistic quantum mechanics, then these are the fundamental constants. Whether the mass of the electron really is fundamental, or the Higgs boson will tell us something more, well, maybe next month we'll find out. I don't know. But for the moment, this is what we got from our fundamental constants in thinking about atomic units. So now we can play some games. This is a numerology game that you all should learn and think about. It's really important. How do we make a characteristic length, a characteristic energy, a characteristic momentum out of these constants? Well, there's some tricks of the trade here. So first of all, h bar has units. H bar is the unit of action, right? The fundamental unit of action. And action is a phase space area. It's momentum times length. It's one way of expressing h bar. So what we're looking for in atomic units is a characteristic length. I'll call that A0. A characteristic energy. I'll call that E0. And whatever else, let's just say momentum. For homework, you'll have some time to play with all of these things. I'll call it P0. So it would be natural then to define whatever characteristic length and characteristic momentum we had, such that P0 times A0 is h bar. Of course, there are factors of 2 pi and whatnot. We're not talking about the exact action for anything. We're saying what's the characteristic scale of things. So now the question you can ask yourself, what about energy? How would I make an energy out of these things? Well, there's lots of ways I could do it. A characteristic energy would be, for example, p squared over m. So that's one way I can make an energy out of my characteristic constants. What about charge and length? Sure. There is the Coulomb energy associated with a charge and a length. Now here you have to deal with one of my fetishes. You'll see many of my fetishes. But one of my fetishes is the tyranny of SI units, which I am a rebel against, because they are just wrong. There is no such thing as epsilon naught. There's no such thing as mu naught. Maxwell proved that. There's the ether. So why in the heck are we still using epsilon naught and mu naught? I have no idea. except somebody in France decided System International, and we all bow our heads. So I'm not bowing. We're going to use CGS units, and you're going to have to learn Sanskrit in this class. So this is on video for everyone to see on the internet. We'll see what revolution we start. But Coulomb energy is charge squared over length. Now, if you are so perverse, you can put a 1/4 pi epsilon naught in there. But if you want to translate, always write epsilon naught as 1/4 pi. Right? So, you know, System International, magnetic field and electric field have different units. They shouldn't. They're the same thing. I mean, in Jackson's book, he changed his, because under pressure, he changed his book to have SI units, but only in the first half. Because now the second half, he changes back to CGS, because if you're going to do relativistic electromagnetism, you can't write the metric tensor with epsilon naught. It's a totally crazy thing. The electric field and the magnetic field should have the same units, because they're the same thing, just in different reference frames. Enough of my rant. All right, so given this, we can then now determine, given these relations, we can determine some of our characteristic scales. So we can plug in P squared here is h bar squared over A naught squared, the mass of the electron, equals P squared over A naught. So that then determines our first unit over here, A naught h bar squared over NE squared. That is a characteristic length that you can make out of these constants. And this, of course, is the Bohr radius, which is approximately a half an inch. Okay. So given that, we can plug A naught into this equation and get a characteristic E naught. And that characteristic E naught is ME to the 4th over h bar squared. And that energy is known in atomic physics as 1 Hartree. Perhaps a less familiar unit, but it's the unit of energy in atomic physics. And the Hartree is equal to twice the Rydberg energy, which, of course, you remember from your earliest modern physics course. And a Rydberg is 13.6 electron volts. So Hartree is twice that, 20s. I can do that math in my head. What's that? 27.2. Okay. So those are two important scales here in the problem. This energy, just by doing this little exercise, we've kind of solved the hydrogen atom. We know kind of what the size of a hydrogen atom is, and we know kind of what the binding energy is of the electron in that force of a proton. So that's pretty cool if we do that. All right, but we're going to get a little bit more quantitative now, thinking about hydrogen. So, the simplest problem in atomic physics to solve, so let's talk about hydrogen, or what I'm going to call, and others call, hydrogenic atom. What I mean by this is the two-body problem of one positive charge and one negative charge, and the quantum mechanics associated with that. So this, what I mean by this is the two-body problem. Right, so what I have here is particle with charge Q1, mass 1, another particle with charge Q2, mass 2, and they're oppositely charged. And they bind to one another. So, for examples of this are hydrogen, the electron, and the proton, singly ionized helium, which is an electron plus an alpha particle. Positronium. An electron plus a positron. All of these are described by essentially the same physics, which is one of the beautiful things. I mean, of course, there are perturbations to all of these that could be different, but the coarse properties have quite a bit of similarity to them. So, of course, the way in which we solve this is to write down the Schrodinger equation associated with this. So this is the two-body problem. We have some origin here. We have R1, we have R2, and we can write down the Schrodinger equation associated with this two-body problem. So, in particular, what we care about is the Hamiltonian. So we have kinetic energy of particle 1, we have kinetic energy of particle 2, and then we have, let me, for simplicity here, make one of these charges explicitly negative by putting a negative sign in front of that. So Q2 is a positive number. So then it's minus Q1, Q2 over minus R2, magnitude, the Coulomb potential in between them. And then, of course, as we know, we can separate this by going to center of mass and relative coordinate. So this is the relative coordinate between particle 1 and particle 2, and this is the center of mass of that two-particle system. Then we can separate the Hamiltonian into the momentum of the center of mass divided by the kinetic energy of the center of mass, and the relative, so this is the center of mass, this the relative over the reduced mass minus Q1, Q2 R, where M is the total mass and mu is the reduced mass. Okay, so in this representation, for the forces that we've included, there's no other additional forces. What we see is that the center of mass is a free particle. And then we have the potential binding or scattering of the two particles in relation to their relative motion. And we'll come back to the quantum mechanical nature of the center of mass of our atom at the end of the semester when we talk about laser cooling. Because typically, the center of mass, if in almost any traditional textbook on quantum mechanics, forgets about the center of mass of the atom. You just, it's treated as a classical position of the atom. And the quantum nature of the center of mass of the atom is typically ignored. Why is that? Why typically do we ignore the quantum mechanical nature of the center of mass? Well, we got this N here. And the masses of the whole atom is, if it's something like standard matter with a proton in it, the center of mass is hugely, thousands of times more massive than the reduced mass. And thus, the wavelength associated with that at normal temperatures is just tiny. And thus, the quantum mechanical wave nature of the center of mass is irrelevant in almost everything until recently, when we can cool atoms to temperatures that are so low that the quantum mechanical wave nature of the center of mass of the whole atom matters. So we'll come back to that later. Okay, so for the moment, though, we're going to, though this, as I said, talk about all kinds of bound to charge systems, Coulombly bound. We're, for the moment, going to restrict ourselves to standard matter. In which we have a nucleus which has atomic number Z and one electron. So this is, for example, hydrogen or singly ionized helium or doubly ionized lithium, etc., etc. Okay. So in this case, the mass, the total mass of the atom is almost entirely the mass of the nucleus. Z, whatever the number of nucleons in the nucleus. And the reduced mass is almost, approximate. I mean, even in hydrogen, where you have 2,000 times the weight or mass of proton versus the electron, is almost the mass of the electron. So in this case, we can think about, in this problem, the center of mass degree of freedom is almost the the nucleus, it's the degree of freedom associated with the nucleus, and the relative motion is really approximately the electron's motion relative to nucleus. So we can think about this as roughly nuclear motion and electronic motion, where now the electron's motion, if this is the nucleus, is measured relative to the fixed nucleus.
Is the point of the center of mass inside the nucleus generally, or is it a little outside?
You'll see that in homework.
Oh, that's all right.
It's actually been interesting. There's recent experiments, brand new experiments, with muonium, which is, a muon is a heavy electron, as you know, bound to a proton, which seem to now dispute what the radius of the proton is. Because if the electron wave function starts to penetrate inside the nucleus, well then this is no longer the Coulomb force, right? I mean, that's some Jackson problem you do. Maybe you'll do that with me next semester, where you have the sphere of charge and you look for what the, the Coulomb energy is outside. So it's going to affect the energy level. That's a slightly different question you asked, is where the center of mass is, but it's interrelated.
Thank you.
All right. So with that said, let's think about now writing. So now I'm going to concentrate on the Schrodinger equation associated with electron motion, which is really the reduced mass motion, but to very good approximation, to the approximation we care about right now. It's the electron motion relative to nucleus. Okay. So in this case, what we have is p squared over twice the mass of the electron minus z e squared over r. Is my Hamiltonian. I'm going to drop my hats because they're too annoying to carry around. All right. And we seek to solve. Let's look for bound states. Of course, there are unbound states too. They represent the states associated with the scattering of an electron off of the nucleus. And that's a whole other important subject that we're not even going to touch on this semester. So we're looking for the states. Let me just remind you, this is the vector p squared of the Hamiltonian with certain energy. Okay, so we're looking for the bound states, and we are choosing the zero of energy associated with the two particles at infinite distance from one another. So that the bound states associated with in this negative energy. So again, the binding energy here is a positive number. So for example, we know in hydrogen that the binding energy when the electron's in its ground state is 13.6 electron volts. But the energy eigenvalue is minus 13.6. Okay. So just to review some things here for everyone. Of course, we can write this, the first, let's see what I want to say here. So the motion is in 3 dimensions, which is why I reminded you that this is a vector. And so there is radial motion of the electron and angular motion. Of the electron. Okay. Great. So, of course, as we remember here, so L here is the orbital angular momentum of the electron relative to the nucleus at the center. And the energy eigenstates of the system are specified not only by the energy, but other quantum numbers which are determined by the symmetry of the system. So, generally speaking, this is an example of a central force problem. Because the force only depends on the distance from the origin and not the direction of the relative coordinate. And because of that, we see some symmetries. In particular, there's spherical symmetry. So, what does spherical symmetry mean? It means that, of course, the system is invariant under rotation about any axis. Which means that there are conserved quantities. In particular, angular momentum is conserved. And that is exhibited by the fact that the Hamiltonian commutes with the angular momentum, its magnitude. So, of course, we have 3 degrees of freedom for the electron, and therefore, in order to specify, we can completely specify and integrate this equation of motion if we have 3 conserved quantities, because that restricts classically the trajectory, and quantum mechanically completely specifies the solution. So, of course, what we know is we can specify 3 conserved quantities in this, for the case of the central force problem, no matter what that central force is. For example, the energy or Hamiltonian, the total angular momentum, and any one component of angular momentum. We can't specify all 3, although all 3 are conserved because, of course, they don't commute with one another. So this is true no matter what central force. We have, of course, a particular, this is right here, excuse me. This is a particular central force problem, the 1 over r potential, which has some very particular and interesting properties, and we'll come to them probably next time. So let me just conclude this lecture by just writing down just a few more things. So if we re-express now our Schrodinger equation in the position representation, then we have the usual expression. Oh, so Schrodinger equation The symmetries of the system, of course, means that we can express our energy eigenstates separated in terms of the radial wave function and our spherical harmonic. Where L squared acting on YLM is the usual eigenvalue. And from this, plugging this in, expressing the Laplacian in spherical coordinates in the usual way. Remind me about that. If I write n without a little subscript, I do mean the mass of the electron. And of course, you remember that this is more simply expressed if I multiply everything through by R. In which case, we define this quantity as the reduced radial wave function. In which case, our Schrödinger equation reduces to a one-dimensional ODE that looks like a 1D Schrödinger equation. So this is the radial equation that we need to solve the Schrödinger equation, and it is the equation for a particle moving on the half-line. Because R cannot be less than 0. That is the magnitude of the relative coordinate. So there is a boundary condition here which says that U has to go to 0 as R goes to 0. Otherwise, the whole thing will blow up. Well, that's not quite true. What I mean to say is you cannot go to infinity. So, the last picture I'll draw here what we're solving is the usual problem you know from classical mechanics of a central force. We have the Coulomb potential, it goes like 1 over R. And then we have the angular momentum barrier, which depends on L, which goes like generally, depending on if L is bigger than 0, will be 3 in a moment. We have h bar squared L plus 1, 2 squared. And then we have the effective potential whose bound states we seek. Okay? So we'll review this and talk about the basics of hydrogen next time. All right? So we're starting off slow, but believe me, fast. All right, have a good day, and I'm available for any other questions. We'll go to the next class. All right, welcome everybody. First day of school. Nervous. This is atomic physics, and those of you who don't know me, I'm Ivan Deutsch. So let's see. First things first. There will be this is the last piece of paper that I will hand out in this class, because all of the information for this class will be distributed through the website for the class. Okay, and you can. I will email everyone who's registered for the course, because then I have your email address on the registration list. The link, but you can find it on the department's website. Okay, so there's a list of classes, and that has everything on it. So let's see. So some first administrative details about the course. So this is an advanced graduate course, and so really it's up to you, from my perspective, to get out of this class what you want to get out of this class. And I assume you're here because this is a subject you're interested in and you like to get as much as you can. So as far as the course requirements go, although you may have seen otherwise, I've made a decision. There won't be any exams in the course. There'll be problem sets, which will be approximately every other week. We'll see how it goes. And there will be, and they will be worth 70% of your grade. Let's see. Finally, I will plan to have at least one office hour, if not an office hour and a problem session or something, to help work through the homework. And so I'll be polling you over email to get a sense of when we might be able to do that, so that we can get the most people available. All right. So, anybody have any questions at all? As far as the textbooks go, so I should say, beyond the book by Chris Foote, there is a book that I call the secondary text here. I meant to bring these to class today, but I'm sorry I forgot. It's a book by Branson and Yohanian. It's called Physics of Atoms and Molecules, and it has a lot of more details in it. It's a book about this thick. Well, of course it has atoms and molecules in it, but it has a lot more details in it. It has quite a different emphasis, but I do recommend it. You know, it's really a question of what reference material you would like to have for your own library. So I won't be following any textbook in any very rigorous order. I have my own idiosyncratic preferences for how to present things. So, but nonetheless, we'll be referring to those things. All right? Okay, well, we'll get started here. All right, so, and then there is a final project which will essentially be a kind of term paper on a subject of interest to you, and that will be 30% of your grade. So as far as the requirements go, in terms of your grade, that's what it is. As far as the material for the course, as it comes, I will post my lecture notes on the web. In addition, we have our great cinematographers here, award-winning, and we will post a videotape, a part of the MP4 for streaming for you to review for the courses as well. Okay. There is a textbook that I called a required textbook, but it's not really required. Again, it's up to you. The textbook is a textbook by Chris Phys. It may just be called Atomic Physics. Let's see what it's actually called. Yeah, it's called Atomic Physics. It is not quite at the right level for this class. It's more of a, and it's as discussed in the preface to the book, it's more of an undergraduate text than a graduate level text. But it covers the range of topics that I'd like to cover for the most part in this course. Chris is a experimentalist at Oxford working on boson-type condensation and quantum control. And so he's what I would call a modern atomic physicist. And that's really what this course is intended to be. Now, of course, that's a pretty loaded word. You know, I'm a modern kind of guy, but, you know, one person's modern, another person's old-fashioned. But my intention here, this course, if you look in the course catalog, the actual title for this course is Atomic and Molecular Structure. It's a little bit of a leftover of olden times. And my intention here is, I've taught a course like that about 5 or 6 years ago. It's the only time I've taught this course before. It was really just a structured course. But I decided to shift gears a little bit. So this course is going to involve a number of topics beyond structure. We'll spend about 1/3 of the course on basic atomic structure. We'll spend about 1/3 of the course talking about the interaction of atoms with electromagnetic fields. A subject which is covered in many courses, including in quantum optics. Those of you who were in quantum optics about a year ago when we taught that, I don't remember anymore. There'll be some overlap there, so it's always good to see some things again. And then we'll spend about 1/3 of the semester talking about laser cooling and trapping. And if we get to it, hopefully, Bose-Einstein condensation and degenerate quantum gases. All right. So that's the intention for the course. The TAs for the course will be the students in my group, so you can harass them, even if they're in the class. And we'll work out other ratings. Let's see. So we're talking about atomic physics. Now, atomic physics, I would say, has kind of two streams associated with it. There's the stream I would call understanding what nature gives us, and the stream, what can we do with nature? And at some level, this dichotomy appears within the AMO physical community. There's a big part of course, atomic physics was what understanding what atoms were, you know, at the end of the 19th century, beginning of the 20th century, is what gave birth to quantum mechanics. The Bohr atom is what I would say the important conceptual picture that gave birth to quantum mechanics and everything that followed it, of course. And this birth, of course, led to the whole history of 20th century physics. I mean, the Rutherford experiment, understanding the nucleus by scattering an alpha particle, you know, that's the LHC, is its descendant today.